Welcome to the debate. We are diving deep into the plumbing of modern AI systems, specifically Retrieval-Augmented Generation, or RAG. For anyone who needs a quick refresher, RAG is essentially the architecture that allows large language models to use external verifiable context to, ground their answers in facts rather than just relying on their training data.
And the quality of that external context is, well, it's everything. Today, we're really dissecting the core architectural tension in building these systems at scale. Where do we place our primary priority? In the structural rigor and connectivity provided by something like a knowledge graph? Or the raw speed and efficiency of a semantic vector store?
My position is, I think, pretty clear. Structural knowledge, which is derived from graph traversal and careful ontological design, is the ultimate driver of RAG quality. It gives us explainability and multi-hop reasoning, the kind of deterministic logic LLMs inherently lack. We're trying to transform retrieval from a simple list of snippets into a reliable reasoning backbone.
And I come at it from a different angle. Structural reasoning is fundamentally useless if the system can't efficiently find the raw material needed to execute that reasoning. I maintain that efficiency and scalability are the foundational requirements. So semantic retrieval, powered by vector similarity search, is the necessary first step. It's optimized for low latency and high volume, what we call coarse recall. And frankly, it's what makes a production system feasible in the first place.
I see why you emphasize speed. I do. But if we look back at the early RAG implementations, the primary weakness was using simple vector stores alone. Similarity is not sufficiency. A document can be semantically similar to your query, but factually irrelevant, or even worse, unverifiable. A graph structure solves this by connecting concepts and tracking entities explicitly. This connective tissue is what enables that multi-hop reasoning, which goes way beyond simple keyword matching.
I'll grant you that the graph provides critical depth, but we have to talk about retrieval latency. For any production system, the time it takes to get context is the single most important quality attribute, full stop. If that process is slow, the user experience is killed. And to handle vast amounts of unstructured text, we need these highly performant approximate nearest neighbor indexes. Essentially optimized databases for finding similar vector embeddings fast. Semantic search captures the messiness of natural language, giving us that crucial, efficient, top-end list of candidates, even when a user phrases a query a bit oddly.
But that top-end list, however quickly you generate it, needs validation. And that's where the graph provides, I think, non-negotiable value. Explicit provenance and trustworthiness. By linking every single fact node back to a source node, complete with properties like a confidence score or relationships like originated from, the graph ensures auditable outputs. You just cannot claim verifiability in sensitive domains, think healthcare, finance, intelligence, without that kind of structural guarantee.
That's a compelling point on auditability, but have you considered that we can incorporate structural information without relying solely on these slow, deterministic graph traversals at query time? We don't have to separate structure and speed,
So, absolutely.
Well, we can actually bake structural knowledge directly into the retrieval layer itself. Algorithms like node-to-vec or fast random projection, these are methods used within graph data science. They generate numerical embeddings that encode structural similarity. They capture how entities relate in the graph topology, which then allows us to solve a structural problem efficiently using that super fast vector lookup. FastRP, specifically, is often used on large graphs because it projects those complex structural relationships into a lower dimensional space, prioritizing efficiency.
That's a clever way to encode structure. I grant you that. But it still feels like we're fundamentally outsourcing the core reasoning to the vector space. That approach is still probabilistic. I think the crucial point here is that deterministic reasoning, the kind enabled by explicit multi-hop logic, is the graph's greatest contribution.
Okay, so why is that deterministic pathfinding so superior in a production environment?
Because it allows a system to derive answers based on explicit logical paths rather than, probabilistic text-based guessing. For instance, You can program the system to understand if drug X treats disease Y and disease Y causes symptom Z, then drug X indirectly alleviates symptom Z. That chain of evidence is derived from traversing specific relationships. This is critical because it means if your input data is X, your logical output is always Y. And that certainty dramatically reduces the risk of hallucination or providing a factually ambiguous response.
I'm still skeptical that this complex multi-hop reasoning is the primary production bottleneck. Let me challenge the sequence here. Multi-hop reasoning is only executed on a small pre-filtered set of passages. Let's say the top 50 candidates returned by the semantic search. The real challenge in a high-volume system is finding those starting nodes efficiently in the first place.
And why is finding the start node the primary bottleneck?
Because you have to make queries start small and fast. If the initial query embedding is inaccurate, or if the vector search itself is slow because of the sheer volume of data, then the multi-hop traversal, it never even receives high-quality candidates to begin its verification process. Latency is always killed by slow initial retrieval, which can take hundreds of milliseconds. That's far more than the subsequent bounded path traversal, which might only take 5. Efficiency drives feasibility.
That's an interesting point about the speed of the initial step, though I would frame the risk differently. The challenge isn't just finding a starting node quickly, it's finding one that leads to the correct path. A pure semantic match, a fast vector hit, could lead to a factual dead end, or worse, contextually irrelevant but similarly worded information. The graph structure ensures that when we match on a node, we immediately know its type, its provenance, and its structural links to other essential entities. The relationship semantics, they guide the next step of the traversal with purpose, ensuring the result set is contextually verified, not just semantically relevant.
Right, so we're clearly converging on the necessity of hybrid retrieval, which forces us to talk about fusion ranking. Advanced RAG systems, they rely on combining signals. The vector score provides the raw semantic relevance and, the initial weight because of its incredible efficiency across vast corpuses. Graph signals then act as crucial filters and boosters.
Explain those boosters. Sure.
The boosters are structural checks, PageRank scores for document authority, recency constraints for temporality validity, or that provenance trust score you mentioned. So the graph's primary value from a high-volume throughput perspective is often realized in refining the candidates that were efficiently provided by the vector similarity search. We want to ensure we aren't wasting cycles pathfinding on low-quality semantic candidates. The vector search gives us 50 candidates. The graph filters them down to the 10 best.
Right, but while the vector similarity provides that relevance signal, the graph signals provide the non-negotiable structural intelligence that guarantees accuracy and prevents contradictory results. This ties back to ontological consistency, making sure your relationships are strictly defined, preventing the data confusion that just arises from unstructured text. Fusing these signals allows the system to prioritize candidates that are not just semantically close, but are structurally authoritative.
Okay, but how do you operationalize that complexity?
We rely entirely on the graph model and the graph data science or GDS algorithms. These are tools that let us run complex calculations, like finding the authority of a node with PageRank or calculating community structure offline. We then store those calculated values as simple properties on the node. So you turn a slow, complex runtime computation into a fast property read. This complex, weighted calculation is essential for factual accuracy, ensuring the LLM relies on verified, reliable evidence, not just relevant text.
That refinement layer is excellent, but it still exists within a scaling constraint. I mean, the sheer volume of embeddings in an enterprise knowledge system often mandates distributing the workload. And this brings us back to predictable performance at scale. For very large graphs, external vector databases, like specialized engines optimized for approximate nearest neighbor lookups, are often more performant than trying to keep all those embedding calculations inside the transactional graph database.
So you're advocating for architectural separation, which, introduces its own complexity. Synchronization, network overhead. I'm not convinced that outsourcing is the only path to predictable performance. Predictable performance relies first and foremost on disciplined modeling and query tuning within the graph itself.
But how do you handle the volume?
We enforce consistency by using uniqueness constraints on canonical IDs like .query unique, and we index frequently queried properties.
And crucially, as I mentioned, we pre-compute heavy structural signals like PageRank offline and store the result as a property. This dramatically reduces the runtime cost of retrieval. In many cases, this makes native graph retrieval highly competitive, particularly when you factor in the network latency of synchronizing between the graph and an external vector store. You gain speed in one place, only to introduce latency in another.
Pre-computing PageRank is a must-do optimization, I agree, but it's still a late-stage refinement. The Retrieval API has to be architected to filter early and cheaply. The proven pattern for scale is coarse semantic recall, a fast vector search returning 50 candidate IDs, followed by precise, quick structural filtering in the graph. If you can't get that initial list back in milliseconds, no amount of structural boosting or indexing will save your end-user latency. We have to respect the scale curve. Optimized ANN indexes are the gateway that makes the entire hybrid system feasible for high-traffic environments.
So, to bring it all back together, my main argument hinges on the fact that the graph provides the non-negotiable elements for enterprise-grade RAG. The ability to explain why an answer was given, auditability, and deterministic reasoning over connected knowledge paths. Without that explicit structure, the relationship semantics, the provenance checks, the LLM is still just reasoning based on weak evidence. The graph transforms retrieval from a gamble into a certainty.
For me, the crucial takeaway is that scalability simply determines feasibility. The ability to serve context with sub-second latency is paramount in production. Vector search provides the necessary speed and breadth of recall, serving as the efficient gateway to the knowledge graph. The ultimate success of hybrid RAG relies on fast semantic selection, followed by quick, bounded graph traversals. That means the foundation has to be built for speed if we ever hope to reach the point where that sophisticated graph structure can even be utilized.
Ultimately, the source material offers concrete patterns for achieving this powerful yet precarious balance. We have to acknowledge that the graph structure and vector semantics must be synchronized and fused using tools like Cypher and GDS to deliver context that is both semantically relevant and structurally verified. The strength of these modern systems lies precisely in mastering that hybrid approach.